let us continue with phase response. So, we saw what the definition of group delay was, and we introduced tau g of omega as being the negative derivative of the phase, and we saw what the physical implication of this is. There is a related concept called phase delay, and this is given by phi of omega by omega, and one of the tutorial problems explores these two concepts in more detail. Suppose you have a narrowband signal, which means it has a certain envelope, and inside the envelope there is a high frequency oscillation, and if you pass this through a general system, you will be asked to show that the envelope gets delayed by tau g and the carrier inside will get delayed by the phase delay tau ph. So, the envelope gets delayed by the group delay, the carrier, the phase, that gets delayed by the phase delay. So, under certain assumptions you can show that this is what falls out if you assume a general system like this. We will not talk about phase delay other than mentioning the definition, whereas group delay we will talk more about group delay as we go along. So, what we have seen so far is phase response in general is nonlinear, and the corresponding nonlinear phase response gives rise to whatever group delay that such a phase response gives rise to, and we saw what the physical implication of group delay is. It delays components. Now, if you recall, so this was the ideal low pass filter, and then we made the statement that the Paley-Wiener theorem does not allow you to realize ideal filters that are causal. So, we saw that the next best thing is to approximate them using a rational transfer function, and such an approximation may look like this. This may be the rational approximation to the ideal filter, that is the rational transfer function approximation to the ideal filter. And we have seen the implications of phase response. So, the question that we would like to ask at this point is, can the rational transfer function approximation be realized with 0 phase? The reason why we are asking this question is, if the phase were 0, then your group delay will be 0. Therefore, whatever delay or distortion that arises out of group delay will not be present. Therefore, it will be nice to have a frequency transfer function with 0 phase, so that you do not have to worry about phase response affecting your output. Now, let us see whether 0 phase transfer function can be realized. So, now let us consider the following. So, you have an input x of n, and then you pass it through a system h of z. Then you do time reversal, then you pass it through h of z once more, and then you do time reversal once again, and then you get the output y of n. Now, let us see what is the consequence of these series of operations. At this point, the output is x of z times h of z. At this point, if you time reverse, you are going to replace z by z inverse. Therefore, you have x of z inverse, h of z inverse. Again, you are filtering by h of z. Therefore, this becomes x of z inverse, h of z inverse times h of z. Again, you are going through one more time reversal. Therefore, at this point, y of z is, now you have to take the input z transform and then replace z by z inverse. Therefore, this becomes x of z, h of z, h of z inverse. So, this is what the output's z transform is, that is y of z is x of z, h of z, h of z inverse. So, this is what we get, and now let us look at the output's frequency response. So, this is nothing but x of e to the j omega, h of e to the j omega times h of e to the minus j omega. Now, if h of n were real valued, then h of e to the minus j omega is the same as h star of e to the j omega. Therefore, y of e to the j omega is now x of e to the j omega times h of e to the j omega times h star of e to the j omega, and clearly this is x of e to the j omega times h of e to the j omega magnitude squared, and immediately you are able to see that this is 0 phase. Therefore, if you design your filter such that this is the frequency response that you finally want, then you would have achieved 0 phase filtering. Clearly, this is too good to be true. So, what is the catch here? So, if this were possible, then 0 phase filtering is possible, then we need not worry about phase response at all. You can then take out the parts of the syllabus pertaining to phase response, right. Very good. The overall system, because of the time reversal operation, is non-causal and therefore not realizable in practice. Therefore, even though 0 phase filtering seems possible, the operations involved require the system to be non-causal, and hence this is not practical. Therefore, you have to deal with phase response. And phase response being nonlinear gives rise to this group delay, and the other important point is that even though the magnitude response may be constant, if the phase response is nonlinear, it can cause wave shape distortion, right. So, the nonlinear phase response can cause wave shape distortion even if the magnitude response is unity. So, it is not just the magnitude response being unity is enough for you to not cause distortion. So, the individual components will go through without any amplitude change, because the magnitude response is unity, but the phase response being nonlinear can cause wave shape distortion, which is something that you do not want. Now, to see this, suppose you have x of n to be cos 0.25 pi n is one component, the other component is 0.4 pi n, and let me pass this through a filter which is all pass. All pass clearly has unit magnitude response. Therefore, if I have this, and therefore, the corresponding numerator, because it is all pass, is this. Now, if I take this signal and then pass it through this all pass filter, if you look at the input wave shape and the output wave shape, even though the frequency response magnitude is unity, because the phase response is nonlinear, this will cause distortion in the output, and the output wave shape will not be the same as the input wave shape. So, let us look at this in MATLAB. So, I have 0.25 pi n plus cos 0.4 pi n. So, I have created 500 samples of this input. So, let me plot a first hundred samples. So, this is my input. So, this is cos 0.25 pi n plus cos 0.4 pi n, and now I am going to pass this through an all pass filter. Therefore, I am going to pass it through this filter, which is exactly what I had written earlier. Numerator is 0.9801 minus 1.4001 z inverse plus z squared, and the denominator is the time reverse version of this. So, I am going to filter it, and now let me plot the filtered output. So, this is let me plot the entire filtered output to point out one thing that if you are not aware, you should know about. So, this is the okay. So, the point I want you to note is that initially the filter is at rest and you are applying this input suddenly. There will be initial transients, and that is why you see here in the beginning there are transients here. And if you recall the response to suddenly applied inputs, you will have output mode will contain input mode plus natural modes. You can decompose this as the steady state response plus transient response. The transient response is given by the natural response of this all pass filter. So, that is what this portion is, and then in this portion you will have the steady state response. Now, let me zoom in here. Okay. Or rather, it is probably better if I plot it separately. Okay. So, plot. Now, let me plot the last 100 samples. So, let me plot from 401 to 500. So, this is the output, and if you look at these two, you see that the wave shape is very different. And there is no way that you can take the output and you can delay it by integer or fractional amount, it does not matter. No way can you make the output and the input align with each other. The gain is exactly 1 at both these frequencies, and yet no amount of delay will cause these two to be, yes. No, they do not look similar at all, no. So, what is it that you think is happening here? Okay, let me, since you think there is a time delay, let us okay, for example, if you notice here, you have something that is here and then it is coming down, whereas here it is, from here it is going up, right. So, it is really not. So, you can try this, you can try various delay factors. Since I have given you what the transfer function is and I have also given you what the input is, no way will you be able to take one waveform and shift it and get the other. The shift can be either integer or integer plus fraction, does not matter. You will not be able to align these two together. Okay, why don't you try it and then you let me know. Since you have the numbers, try it and then see whether you are able to match it. Remember, if you are able to match it, you should be able to match it precisely, not approximately, all right. So, if you pursue this example more, you will convince yourself that even though the magnitude response is unity, there is still wave shape distortion. You cannot do away with the wave shape distortion that this nonlinear phase response gives you. Therefore, in general we have seen that zero phase filtering is not possible. So, you have to deal with phase response, and magnitude response being unity is not enough. The nonlinear phase response can cause wave shape distortion. Now, suppose y of n is x of n minus n naught, then this, strictly mathematically speaking, the output is not identical to the input, but the output and the input are related by a mere delay. Therefore, the above is a benign distortion called delay distortion. So, if you filter the input by a system, since you cannot have zero phase is ruled out because it leads to non-causal operation. If you had non-zero phase, then you will definitely incur some distortion at the output, but if this distortion happens to be delayed distortion, then this distortion is benign. So, the output and the input are identical except for a delay. So, this delayed distortion preserves wave shape. Therefore, it is really not a terrible distortion. Therefore, we ask the question, what kind of phase response will give rise to this kind of delayed distortion? And again, let us take the simple 2 component cosine to give a feel for what is going on. Suppose you have x of n and you had cos omega naught n plus cos omega 1 n, and if y of n is x of n minus n naught. So, this is cos omega naught n minus omega naught n naught plus cos omega 1 n minus omega 1 n naught, and this is nothing but cos omega naught plus phi naught plus cos omega 1 n plus phi 1, and you are able to see that this phase is proportional to frequency, right. This phase is clearly proportional to frequency. Hence, from this simple example, as an illustration of the general principle, we state that hence if the phase were strictly linear, then we will get only delayed distortion and wave shape will be preserved. And wave shape will be preserved. And this can also be inferred from the definition of group delay. If the phase response is piecewise linear, then the group delay will be constant, and hence if the input has components that falls in the passband of the filter where the gain is nominally 1, if the phase were linear, then the output will be just a delayed version of the input. Because the phase is linear, the passband being nominally 1 means the gain is 1, therefore the gains are not altered for the individual components, and the output is merely a delayed version of the input for those components falling in the passband. Yes. No, because all we are doing is we are replacing n by n minus n naught. So, you replace n minus n naught in both of these terms. So, you get omega naught n and omega 1 n, but the delay when you replace n by n minus n naught, the phase component is omega naught n naught and omega 1 n naught in for these two cases. So, this means that this phase is proportional to frequency. Therefore, you can think of the phase response as being linear, right. So, you were saying right. So, this is indeed correct, right. Yeah. So, all this tells you is if the phase response were linear, then all the components get shifted by the same amount. Therefore, the higher frequency signal, when it gets shifted by the same number of samples, the corresponding phase change will be proportionally be more. Therefore, if the phase response were linear, then you can expect the input to be merely delayed, which also is consistent with the fact that a linear phase response gives rise to a constant group delay. Okay. So, this is the motivation for you to think about systems having linear phase, because they have the advantage that they will only introduce delayed distortion. Zero phase is not possible, not realizable. If you have nonlinear phase, you will have wave shape distortion. If the phase were linear, you can have only delayed distortion, which is benign. So, this is the motivation for looking at linear phase.